In this video, we're going to continue the discussion of power series functions. Given the geometric series, summation n equals 0 to infinity, x to the power of n is equal to 1 divided by 1 minus x. For absolute value of x less than 1, the radius of convergence of this geometric series is r equals 1. Find the sum of the following series. Question A, find the sum of summation n equals 1 to infinity, n times x to the power of n. Question B, find the summation of n equals 1 to infinity, n squared times x to the power of n. Question C, find the sum of summation n equals 1 to infinity, n squared divided by 2 to the power of n, and summation n equals 1 to infinity, n squared times 1.1 to the power of n. Let's start with question A first. Let's start with the summation n equals 0 to infinity, x to the n is equal to 1 over 1 minus x. So this is a geometric series. Let's differentiate both sides and take the derivative of both sides. So d dx of summation n equals 0 to infinity, x to the power of n is equal to d dx of 1 minus x to the power of minus 1. And differentiating this summation, bring the derivative inside the summation, apply the power rule, we get n times x to the power of n minus 1. N equals 0 makes no contribution to this term because we just get n times 0. So just start this index at n equals 1. Now apply the power rule and the chain rule. Bring the exponent down, so we get negative 1 times 1 minus x to the power of minus 2, and apply the chain rule to the inside, differentiate 1 minus x, that gives us negative 1. That's the derivative of the right-hand side. So what we have is summation n equals 1 to infinity, n times x to the n minus 1 is equal to negative 1 times negative 1 is plus 1, and we can write 1 minus x to the power of minus 2 as 1 over 1 minus x squared. All right, so we now have the power series representation of summation n equals 1 to infinity, n times x to the power of n minus 1, and the radius of convergence does not change because when we differentiate a power series, we get another power series, but the radius of convergence does not change. So the radius of convergence is still 1, and the interval of convergence is x between negative 1 and 1. Now, we need summation nx to the n. N equals 1 to infinity. So how can we achieve that? Well, we can multiply both sides by x. So let's do that. Let's multiply both sides by x. X times summation n equals 1 to infinity, n times x to the power of n minus 1 is equal to x times 1 over 1 minus x all squared. So simplifying this x gets multiplied inside the summation, and we get summation n equals 1 to infinity, n times x to the power of n. And this is equal to x divided by 1 minus x to the power of 2. So we now have the power series representation of what we're after, which is summation n equals 1 to infinity, n times x to the power of n. All right, so what we have found is summation n equals 1 to infinity, n times x to the power of n. Let's expand out this series term by term. Plug n equals 1, and we get x. Plug n equals 2, we get 2x squared. N equals 3, we get 3x cubed. N equals 4, we get 4x to the fourth. The sum of this infinite power series is equal to x divided by 1 minus x to the power of 2. The radius of convergence is 1. That means the interval of convergence is x less than 1, larger than negative 1. Recall, if we differentiate or integrate a power series, we don't change the radius of convergence. If we multiply by x or x squared or some power of x, also we don't change the radius of convergence. So to summarize, we have found the sum of the power series, summation n equals 1 to infinity, n times x to the power of n, to be x divided by 1 minus x to the power of 2. And since the original series, summation n equals 0 to infinity, x to the power of n is equal to 1 divided by 1 minus x, is a geometric series with radius of convergence equal to 1. The radius the radius of the convergence of the new power series for summation n equals 1 to infinity n times x to the power of n is also r equals 1. That means the interval of convergence is x less than 1, larger than negative 1. All right, now for part B, we need to find summation n equals 1 to infinity n squared times x to the power of n. So it's logical to start with the result of part A and differentiate, because if we differentiate this summation, we're going to get n squared times x to the power of n minus 1. So that's a good starting point. So let's take the derivative, d dx, of summation n equals 1 to infinity n x to the n is equal to d dx of the right-hand side, x divided by 1 minus x to the power of 2. Now, when we differentiate the summation, we apply the power rule. We get summation n equals 1 to infinity. Bring the derivative inside the summation and differentiate x to the power of n. So we get n times n. That gives us n squared. Subtract 1 from the exponent. We get n squared x to the power of n minus 1. On the right-hand side, we have to apply the quotient rule and the chain rule to differentiate this. So applying the quotient rule, we square the bottom. 1 minus x squared. Squared becomes 1 minus x squared to the power of 4. 1 minus x to the power of 4, and take the bottom, 1 minus x squared, times the derivative of the numerator, that's 1, derivative of x is 1, minus the numerator, which is x, times the derivative of the denominator, which is 2 times 1 minus x, times the derivative of the inside because of the chain rule, that's minus 1. If we simplify all of this, do some algebra, we get 1 plus x divided by 1 minus x to the power of 3. Now, if we look at this, we realize that it's not exactly what we need. We need summation n squared x to the power of n, and here we have summation n squared times x to the power of n minus 1. So multiply both sides by x. Let's do that. So we get x times, let me change color, x times summation n equals 1 to infinity n squared x to the power of n minus 1 is equal to x times 1 plus x divided by 1 minus x to the power of 3. Now let's simplify. X gets multiplied inside the summation. The bases are the same. Add up the exponents. We get summation n equals 1 to infinity n squared x to the power of n, and this is the power series for which we're looking for the function. This is equal to x times 1 plus x divided by 1 minus x to the power of 3. So this is the power series, the infinite power series, and the sum of this infinite power series is represented by this function. This is a closed formula for the sum of this power series. But very important, the radius of convergence is the same as the original geometric series, so x has to be between 1 and negative 1. The radius of convergence is 1, and this is the interval of convergence between negative 1 and 1. That means this function only represents the sum of this infinite power series for these values of x. The values of x have to be in this interval. If they're outside this interval, we can't use this summation to represent the sum of this power series. All right, so what we have found is summation n equals 1 to infinity n squared x to the power of n. Let's expand this out. Plug n equals 1, we get 1 squared times x to the power of 1, plus n equals 2, we get 2 squared x squared. Plug n equals 3, we get 3 squared x to the power of 3, and so on. And the closed form for this for the sum of this infinite power series is x times 1 plus x to divided by 1 minus x to the power of 3. So we found this summation, we found the sum of this series, and the radius of convergence is radius is equal to 1. The interval of convergence is x less than 1, larger than negative 1. All right, part C asks us to find summation n equals 1 to infinity n squared divided by 2 to the power of n, and summation n equals 1 to infinity n squared times 1.1 to the power of n. From part B, we found summation n squared x to the power of n equals 1 to infinity to be equal to x times 1 plus x divided by 1 minus x to the power of 3. For absolute value of x less than 1, this is the interval of convergence, x less than 1, larger than negative 1. Now let's rewrite summation n equals 1 to infinity n squared divided by 2 to the power of n as summation n equals 1 to infinity n squared times 1/2 to the power of n. So you can see that the value of x that's getting plugged into the power series is x equals 1/2. So let's plug x equals 1/2 inside this power series, summation n squared, x to the power of n equals 1 to infinity, and this is equal to x times 1 plus x divided by 1 minus x to the power of 3. We're going to plug x equals 1/2 and find the sum. We're able to find the sum because x equals 1/2 is inside the interval of convergence. X equals 1/2 is inside negative 1 and 1. For this reason, we can find the sum. Let's plug x equals 1/2. We get summation n equals 1 to infinity n squared times 1/2 to the power of n. This is equal to 1/2 times 1 plus 1/2 divided by 1 minus 1/2 to the power of 3. Let's do some algebra on this. We get 1/2 times 1 plus 1/2, that's 3/2. 1 minus 1/2 is 1/2 cubed is 1/8. If we simplify this, we get 6. So this entire series, the sum of this infinite series is just 6. N equals 1 to infinity n squared divided by 2 to the power of n. This is equal to 6. So very important, we were able to plug x equals 1/2 because x equals 1/2 is inside the interval of convergence from negative 1 to 1. So the key idea here was summation n equals 1 to infinity n squared times 1/2 to the power of n is the value of this power series summation n equals 1 to infinity n squared times x to the power of n evaluated at x equals 1/2. And since we have a closed formula for the sum, summation n equals 1 to infinity n squared x to the power of n is equal to x times 1 plus x divided by 1 minus x to the power of 3. We can simply plug in x equals 1/2 and find the sum. All right, now let's find the sum of summation n equals 1 to infinity n squared times 1.1 to the power of n. So the power series that we found was summation n equals 1 to infinity n squared x to the power of n is equal to x times 1 plus x divided by 1 minus x to the power of 3. We cannot plug in x equals 1.1 because x equals 1.1 is outside the interval of convergence. X equals 1.1 is outside the interval of convergence, negative 1 to 1. All right, so that means that summation n equals 1 to infinity n squared times 1.1 to the power of n diverges. That means the sum goes to infinity. So let's summarize. We can plug in x equals 1/2 into summation n equals 1 to infinity n squared times x to the power of n is equal to x times 1 plus x divided by 1 minus x to the power of 3 to find the sum of this power series because x equals 1/2 is inside the interval of convergence x larger than negative 1 and less than 1. But we cannot plug in x equals 1.1 to find the sum of the power series since x equals 1.1 is outside the interval of convergence x between negative 1 and 1. All right, thanks.